Hello everybody, welcome and thank you for joining me today. So I'm going to start this with a nice cartoon for you. I hope everyone finds this really funny. So of course this is a transform boundary, so we call them faults oftentimes. That's where we have two plates moving next to each other, side by side, grinding apart, causing earthquakes and stuff. You all have been doing a great job analyzing some evidence that supports the theory of plate tectonics. So the theory of plate tectonics was a widely accepted theory only in about 1965-ish. So in the 1960s and 70s was when this theory became a true scientific theory. So this is true using all of the evidence that we have available to us. So you have analyzed some of the real data that was used to come up with this theory. So magnetic reversals on the ocean floor out by the Juan de Fuca plate. You've looked at mountain building out by the Himalayan mountains where we have two continents crashing together. You've looked at mid-Atlantic ridges. So you've looked at the age of rock on either side of a ridge, and you've noticed that it's symmetrical. So that suggests that these plates are moving apart and new crust is being formed continually at this. So this is page 5 of your reference table. So this is in your ESRT. You get to use this on every test, even the Regents exam. So in our keys here, so whenever we have these little blocks that look like, I guess, railroad tracks or something, these are convergent boundaries. So this is along the South America, the west coast of South America. We have it up here by the Aleutian Trench, and over here at the boundary between the Eurasian plate and the Indo-Australia plate. So convergent boundaries are where we get our volcanic island arcs. It's where we get our mountains, usually in the middle of the ocean. And these are our ocean mountain chains, right? So these are where we have our plates moving apart, getting pulled apart, and causing underwater ridges to form, which are underwater mountain chains. So there is no denying that the Earth's crust is broken into chunks, which we call lithospheric plates or tectonic plates, and there is no doubt that they are moving. They're moving very slowly, probably about the same rate as your fingernails grow, but they are moving nonetheless. But what is causing this motion? How can we explain this motion? How is this happening? So in class today, we did this demo. So I had a fish tank filled up with some water, and I have a hot plate right underneath here. So this hot plate is heating up the bottom of the fish tank and heating up the water molecules here. So as I dropped the food coloring into the water, they immediately sank. And that's because the temperature of the food coloring is cooler than the water. So that means the spacing between the molecules is closer together and you have sinking. So the density increases with decreasing temperature. But as this water moves towards the center of the fish tank here, those water molecules heat up and the spacing between the molecules increases, which decreases the density. And that's what gets this rising motion here at the center. So this is called a convection cell or a convection current. And the driving force of convection is heat. So as heat is added to a substance, added to a liquid or a gas, those molecules in that liquid or a gas get excited and they speed up, they spread out, and they increase. Right? So as they increase and go up to the top, they start to lose their heat energy, right? And they cool off, the spacing between them come closer together, and the density will increase, which causes this circular motion. So this demo is great because, for the most part, the green and the red do not mix. So you have these distinct convection cells happening here, right? So if we were to think about the Earth's surface, this would be our mid-Atlantic ridge. So this is where new crust is being formed, and the plates that are on top of the asthenosphere are moving side to side away from it symmetrically. So if we take what we just saw in our fish tank and apply it to a model of the Earth, this is what we have. So the Earth's crust is very thin and it's broken up into our tectonic plates, and that sits on top of a liquid or a plastic asthenosphere. So that's our liquid mantle, the looser mantle. So heat moves through the mantle through convection. So it moves those water molecules around and you get this circular motion. So here would be the center of our fish tank, right, where we had our rising water, and then we had our tops moving apart, right? So this is where we have our mid-Atlantic ridge where plates are moving apart. And anywhere we have plates moving apart, somewhere else plates must be coming together. So this is, showing where we have our trench. This is a convergent boundary with subduction. So as this circular motion within our asthenosphere cycles like this, it pulls our plate this way and it eventually pulls it down. So this is our best explanation for how the plates are moving on top of Earth's surface. So main takeaway here. Heat is being moved from the center of Earth, where we have radioactive decay of elements. It's moving up, causing a density difference here. So we have lower density here, higher density out here, which causes motion. And this is how we get motion of our plates. So where else is convection observed? Where else do we have heat being transferred through a liquid or a gas, causing different densities and causing motion? So far we've talked about plate tectonics in the lithosphere. How about the atmosphere? So let's think back to our weather unit. So this is a very simple diagram of convection currents within an air cell. So as the sun beams down onto the surface, it heats up the surface, which heats up the air close to it. So as that air heats up, it rises, right? So the spacing between those air molecules spread apart, lowers its density, and it rises. So as that air rises, it gets higher into the atmosphere where it's cooler, cools down that air parcel, and all of the water vapor molecules that is in that air will condense, which forms our clouds and storm systems. So without rising air, you will never have clouds. So that's why we have low pressure systems. That's when we have most of our clouds and our rain. So as this air cools down, it increases in density and falls back down to the surface, and then you get this constant cycling for when that heats up again. So if we look bigger picture of the Earth, we have our planetary winds and our Hadley cells. So this is our explanation for our global climate. So why do we have rainforests near the equator, and why are most of our deserts at 30 north and 30 south latitude? Well, what we know from our knowledge of the sun and the earth, we have a high angle of insolation at the equator. So that means there's a higher angle, so more direct sun rays hit the equator. It's not that the equator is closer to the sun, because that's not true at all. It's that they get more direct sunlight, is why the equator is the hottest place on Earth. So the fact that there is high insolation here means that there's a lot of warm rising air at the equator. So with warm rising air, you get cloud formations and rain. So this is a humid climate at the equator, pretty much uniform around the globe. But on a larger scale, as that air rises, it'll eventually cool and you get sinking. So you have sinking down at 30 north latitude and you have sinking air at 30 south latitude. So as this air sinks, this cool air sinks, it warms up. And the fact that it's sinking, you don't have rising air, right? So you can't possibly have clouds. So that's why most of the Earth's deserts are at 30 south and 30 north latitude. So I like to use the example of the continent of Africa. So there's the famous Congo rainforest in Africa, and it's a very humid, very wet, and green place. That is exactly at the equator. So that's one of the biggest rainforests in the world. But then on the same continent at 30 degrees north, you have the largest desert in the world. That's the Sahara Desert. And that has to do with these Hadley cells, so the general atmospheric circulation that is happening here. The equator has warm rising air, which allows for clouds to form, and that is not happening at 30 north and 30 south. So we also have rising cells at 60 degrees north, so we're just south of that, so we still have a generally humid climate. And then at the poles, you have sinking air. So the poles are the driest places on Earth. So think about Antarctica. That is the driest desert on Earth. It's an ice desert. But I know what you're saying, Mr. Sommer, but there's a whole lot of snow. It must be pretty humid there. Well, the fact is that it is very dry, but the fact that Antarctica is so cold, whatever snow that does fall there will not melt. So that whatever snow falls will pretty much stay there for eternity. So that's why there's so much snow, even though it's the driest place on Earth. So I have some conclusion questions here for you to answer in your composition book and to bring to class with you next time. So what is the primary force driving plate tectonics and atmospheric circulation? So for question 2, I want you to explain how heat energy is transferred through liquids and solids. So what is the process there? How does that heat transfer affect density? And how does that result in motion or circulation? And for that third question, where else can you see convection being observed within Earth systems? So in this video, we talked about the lithosphere and the atmosphere. What other sphere of Earth could you possibly observe convection in? So thank you for watching this today. I hope you enjoyed this and found this helpful, and I will see you in class soon.